Okay, I think we're good to get going.
All right. Good morning and welcome to the first Maricou's Science Talk. The point of these talks is to highlight the great research going on in the Mid-Atlantic. This session is being recorded and the recording and slides will be posted on the Maricou's website. Please keep your cameras off and microphones muted during the presentation. There will be time for discussion and questions after the presentation. Today we are featuring Dr. Daniel Wang as he talks about the impact of canyon upwelling and downwelling in the Mid-Atlantic Bight. Dr. Wang earned a PhD in marine science from Virginia Institute of Marine Science, William and Mary in May 2021. And he's currently working on thermal lag corrections to glider CTD data for the Maricou's glider team. Take it away, Daniel.
Thank you. Good morning, everyone. Thanks for spending your time here today. In the next 20 to 30 minutes or so, I will show you some of the work I did in my dissertation. Before I start, I would like to thank all the funding agencies that supported me through graduate school, in particular Maricou's and WIMS, ELS, and also William Mary. As we all know, the Mid-Atlantic Bight is a very important region. The coastal ocean here supports nearly 80 million people, and it supports all sorts of economic and recreational activities. And in the coastal ocean here, the properties of the water over the shelf and slope and further offshore are quite different. In general, we have a relatively fresh and colder shelf water and warmer and saltier slope water. And shelf slope exchange is one of the biggest topics in the regional oceanography here. Shelf slope water exchange is a very important topic because the water exchange impact the transport of heat, salt, sediment, pollutants, nutrients, and also it has impact on weather, climate, ecosystem, and fisheries. So here we're looking at two examples of the biological side of the shell break region here. On the left panel here, you're looking at the primary production. And clearly there's a enhanced region of high primary production near the shell break. On the right here, you are looking at the biomass of sea scallop based on a survey that was done in 2013. And also there's some high biomass near the shell break region, and in particular near some of these canyons. So in my research, I focused on the impact and hydrodynamics of the submarine canyons between Virginia and New York. In this region, we have 5 major shell break canyons and quite a few smaller slope canyons as well. And they are almost evenly distributed along the shell break here. And these canyons are interesting in many ways. They have unique and interesting ecosystems. Different organisms live inside these canyons. And also they are associated with some important commercial fisheries such as sea scallop and also recreational fisheries for many fishes like tuna. And also they have interesting geologies. But in my research, I'm asking the question of how do canyon upwelling and downwelling impact shelf slope exchange and shelf hydrography. And this is mainly a physical oceanographic research. So we are all familiar with the traditional coastal upwelling and downwelling. And that's a wind-driven response. So if we have long shelf wind goes with the coast to its left, we're gonna have coastal upwelling, which is characterized by those up-tilting isopeak nodes toward the coast and dense water coming on to the bottom of the shelf. Vice versa, if the wind blows in the opposite direction, we're gonna have coastal downwelling. Canyon upwelling and downwelling are different from the coastal wind-driven upwelling and downwelling. So these processes are driven by along shelf currents. Generally in the northern hemisphere, if we have along shelf currents goes with the coast to its left side, we'll have a canyon upwelling response. And vice versa, we're gonna have a downwelling response. In general, a lot of idealized modeling studies focus on canyon upwelling because upwelling causes more night cross-shelf water exchange. And canyon upwelling is a three-dimensional process. And one result of canyon upwelling is the dense water from the slope will be upwelled onto the shelf and forms these pools of upwelled water at the outer shelf here. And in the rest of the talk, I will refer to this water as canyon upwelling plume because of the shape of them. And what you look at here is, so this is a schematic from Ramos Muslim et al. Dissertation. And this is a laboratory experiment that she did. And clearly you saw those upwelling plume at the bottom of the shelf there. So coming back to our region. So we all know that the mean ocean circulation is that the current goes to the southwest or equatorward with the coast to its right-hand side. And in the context of canyon upwelling or downwelling, that means the currents are favorable for canyon downwelling. But we were wondering, can upwelling events occur in our region? And can we actually get some direct evidence of canyon upwelling here? So in the past few years, with the support from Marcus, we have performed 4 glider surveys in 3 different canyons of the coast of Virginia. And in this talk, I'll focus on the survey we did in 2016, which gave us the most clear evidence of canyon upwelling. So this was the survey pattern we did. So we have a few repeated transects in the along canyon direction, also in the cross canyon direction. And now you're looking at the results from 3 consecutive cross canyon transects that are almost parallel to each other. So on 3 different days. And here you are looking at the distribution of temperature is being interpolated. And the wet tracks here are glider survey tracks. What you can see here is that we have a 3-layered water column structure, and they are associated with 3 different types of water masses. So in the upwelling period, what we see is this cold water inside the canyon went up from this transect to that transect. And then in the downwelling period, that water went down again. And that happened in the time scale of about 10 days. And likewise, in the along canyon transect, 3 consecutive along canyon transect, we also saw evidence of upwelling and downwelling. So in the upwelling period, the evidence is that the isopycnals, also the water masses here, it tilted up from offshore to the shelf. So upwelling period tilted up. And then in the downwelling period, the isopycnals and water mass just tilted down. So these are pretty clear evidence that we captured a consecutive kind of upwelling event and downwelling event. And the downwelling occurred right after the upwelling event. And then in order to put the glider observations in a larger spatial and temporal context, we further did some numerical simulations. In the model we used, it's called Schism. It's an unstructured grid model. And on the left here, you are looking at the model domain from Cape Cod all the way to South Carolina to Georgia, covering the entire MAB. And in terms of the model resolution, we put a really high resolution along the shell break in order to resolve the canyon and shell break processes. And for the most part, the resolutions are about 400 to 500 meters in the southern MAB, and near the Hudson Canyon, the resolution is about 800 to 1,000 meters. And on the right here, that's just an example of what the horizontal grids of the model looks like. So these are unstructured triangle grids over the Wilmington Canyon here. And with this high resolution, we're able to resolve the processes that occur inside the canyon, also along the whole shell break. And in the vertical direction, we have up to 55 vertical layers with intensified resolution near the surface and bottom. And also, we put a bunch of realistic forcing conditions to force the model, such as a high resolution bathymetry, we put tides and temperature, salinity, velocity data from HICOM, wind data, and also freshwater discharge from some of the major estuaries. So let's see how the model did. So here is an comparison between the observation and the model. The top panel, top row here, you're looking at the data from the glider. So these are just those V-track visualization of the glider data. And the bottom here is the result from the model. And the takeaway message is that the model recaptured the same water column structure and same water masses as the observation. And that's sufficient for the purpose of our research. And also, at this instance, we were having upwelling, transect upwelling event, and the model also captured that upwelling event. And if we inspect more from the model results, we see that in the upwelling period, the vertical velocity inside the canyon is upward. So the red color here is upward velocity inside the canyon. And the dashed line here, that's the location of the head of the canyon, and that's the mouth of the canyon. So we have this upward velocity inside the canyon during the upwelling period. And in the downwelling period, so that day was a transitional day, but on this day, very strong downwelling occurred inside the canyon, near the bottom of the canyon. And then if we inspect the time series near the head of the canyon and trying to make sense of what happened, we look at the wind condition, cross-shelf, sea surface height gradient, and compare that with what happened with the current velocity inside the canyon, and also temperature and density at the head of the canyon. So during the upwelling period, we had wind coming from the northwest or southwest, westerly winds. So that's upwelling favorable. And the sea surface height gradient was positive, which means that the sea surface height was lower near the coast and higher offshore. So that's upwelling favorable condition. And indeed, inside the canyon, we had upward vertical velocity and also northeastward horizontal velocity. Those are the blue vectors there. And in the upwelling period, the temperature dropped, the blue line here, and the density increased at the head of the canyon. So all those are upwelling signals. And in the downwelling period, we saw the opposite trend. And the upwelling event actually lasted for 9 days in this entire period. And if we take a broader spatial view, so of what happened. So right now we're looking at the bottom horizontal velocity in vectors and also density distribution. So this is the Wilmington Canyon, the canyon here. This is the Baltimore Canyon. So in the beginning, there was not much going on. And then once upwelling started, we start seeing the development of this upwelling plume at the bottom of the shelf, which was sustained for over a week. And then on this day, upwelling stopped, downwelling began, and we saw that upward water just disappeared from the shelf. And if we pay attention to the spatial scale of the plume, so the canyon, Wilmington Canyon itself is about 20 kilometers long, 10 kilometers wide. So the plumes actually much longer, much greater than the size of the canyon in terms of the horizontal coverage. And if we were to look at some transects along the plume during the upwelling period, so there's 3 different days in the upwelling period, and we will inspect the results along these 3 transects here. And we see that the cold water from the canyon, from different stages of the upwelling event, they developed onto the shelf. So from here all the way to there. And so that's the along plume transect or along shelf transect. This is a cross shelf transect at the head of the canyon. And we see that, so this is where the head of the canyon is. The cold water went onto the shelf right at this location. And that's sort of a dome shaped. And if we were to examine the thickness of the plume, it's about 20 to 30 meters thick. And there's another result from the model that's interesting to us. If we examine the velocity distribution associated with the upwelling plume, in the along shelf velocity distribution, we see that on the left hand side of the plume, because the plume here goes into the page, So that's the positive direction. We have this bottom intensified jet, and that's a baroclinic jet because that's associated with the dense water effect of the plume. So these are two different crowd-strap transects, and they exist on both transects. And then during the downwelling period, that plume water disappeared from the shelf on different days. And that's just showing that the water quickly disappeared from the shelf through the course of the downwelling event. And one upshot of this quick downwelling response was that there was a very strong bottom intensified down canyon current inside the canyon. So we're looking at the along canyon velocity here distribution, and the positive is to the right hand side. So that's down the canyon. So there's a near bottom currents here going down the canyon, and this is the vertical velocity. So that's very strong downward velocity here. And that's of course associated with the movement of the water. And so here we're looking at temperature. So that's one takeaway message in the downwelling event. We have that strong down canyon current. It is a schematic that I drew by hand. So in the upwelling period, we see the slope water coming onto the shelf and got advected down shelf in this very strong baroclinic jet. And in the downwelling period, those water will go back, and most of them go back in. Most of those parcels of water go back into the canyon and cause this very strong down canyon current inside the canyon. And if we look at the results in a larger spatial perspective, the downwelling or the canyon upwelling plumes actually developed at all the canyons. So here's on one of the days of upwelling. And so that was, this is Women Canyon and all the other canyons in the region. So we actually had canyon upwelling plume developed at all those canyons. And the upwelling period was associated with a sea surface height distribution in a way that it was lower near the coast and higher near the shelf break. And these are wind stress, just showing that the wind was upwelling favorable. And then likewise, downwelling also occurred at all the canyons in this particular event. And then we also did a much longer model run. And we got some good input data only from January to April of that year. And after that, there was some problem with the input data. And so we only got the results from January to April of 2016. But within that, a little bit over 3-month period, 3.5-month period, we had about 12 cycles of subtidal upwelling and downwelling. So here we're looking at the vertical velocities near different canyons, at the height of different canyons. So if it's below 0, that means there was downwelling going on, and above 0 means there was upwelling going on. And one interesting result here is that the cycles of upwelling and downwelling occurred coherently in space. So at these different big canyons, from Norfolk Canyon to Hudson Canyon, those 5 major canyons, upwelling and downwelling almost always occurred simultaneously at those different canyons. And the correlation coefficient is somewhere between different canyons, is somewhere between 0.83 to 0.96. So that's, and the rule of thumb here is that if they are further away from each other, so such as Norfolk Canyon in the south and Hudson Canyon in the north, that the correlation gonna be lower. But if it's Norfolk Canyon, Washington Canyon, which are very close to each other, the correlation gonna be high. And that's here, that's just the near bottom temperature at the canyon heights for the same canyons. And at these different cycles, we see that the cold plumes develop during each upwelling phase of the cycle, and it will shrink at each downwelling phase of the cycle. But that canyon upwater almost never completely disappear from the shelf, because usually before the downwelling can bring all those canyon upward water away from the shelf, the next upwelling event would occur, at least during this period. So upwelling period, we have those cold plumes on the shelf. Downwelling period, they shrink a little bit. Upwelling period, they grow again. Downwelling period, they shrink again. And then the next thing we did was to do a hypothetical no canyon experiment. So in the canyon case, we kept the bathymetry of all these canyons. In the no canyon case, we replaced the bathymetry in this rectangle here in the southern part of the region with just regular shell break bathymetry. So smooth those canyons out. And if we compare the results from the control case and the no canyon case, we see that those plumes which either disappeared or much smaller in those modified region. But if in the Hudson Canyon region where we didn't modify the bathymetry, the plume still developed there. So here is the bottom temperature, and then if we do the difference between the two cases, so that's the case with the canyon, the control case minus the no canyon case, and then we see that and the different conditions. So this is the upwelling condition, downwelling condition, also all time within that 3.5 months. We see that, so this cold water, warm water, cold water anomaly at all these canyons. And the takeaway message here is that the existence of the canyon bathymetry cause cold water anomaly. And if we look at the cross-shelf transect, so this is a cross-shelf transect away from Wilmington Canyon, a little bit north of Wilmington Canyon, we see the same thing. So in the case with canyon, we see this cold water, this length of cold water, which is result from this canyon upward water that got advected downstream. We see that in the canyon case, but in the no canyon case, we barely see that signature there. So this condition is when we had upwelling favorable conditions. That's when we had downwelling favorable conditions. That's just all time. And if we look at the difference between the two cases, we see this cold anomaly again. And the anomaly is bigger in the upwelling conditions, which makes sense because canyon upwelling brings those cold water onto the shelf. In the downwelling case, there was still some cold water anomaly, and that is because that upwelling water from the upwelling period was still on the shelf. And that's the all conditions. And if we examine the velocity distributions, so that's the bottom velocity. The arrows are showing you directions, and the colors shows you the strength of the currents. So in in the upwelling condition, we had the currents going towards northeast. And downwelling conditions, they went southwestward. And then if we compare the canyon case with no canyon case, it's a bit hard to see just based on this alone. But if we subtract this from that, that's what we'll see here. So that's the difference in speed. So in the upwelling case, we see those. So in speed, if it's blue, it means the anomaly is northeastward. So that means the canyons. If it's red, it means northeastward. That means on the shelf here, the canyons caused northeastward anomaly. In the upwelling case, I think. All right.
Haijin, just want to let you know it's been half hour. So
Yep, I noticed that. Yeah. So I have two last slides. And then the last thing we did was, so we checked the correlation between cross-shelf surface height gradient and the occurrence of canyon upwelling and downwelling. So also with wind. So the blue time series here is the vertical velocity at the height of Washington Canyon, and the red arrows are wind vectors here. And the bottom here is the cross-shelf surface height gradient with the vertical velocity at the height of the canyon. And we saw a really good correlation between the cross-shelf surface height gradient and canyon upwelling or downwelling. And then we think that's a good indicator that we can use to estimate the long-term occurrence of canyon upwelling and downwelling in the region. So we used a long-term sea surface elevation output from HICOM, and we calculate the cross-shelf surface height gradient. And we use that. If it's positive, it's going to be favorable for canyon upwelling to occur. If it's negative, it means it's favorable for downwelling to occur. So very simple criterion there. And the result we got was, first of all, downwelling is more common than upwelling in our region, but upwelling is more common in the wintertime and also in July. So there's some seasonal variations there. And it's actually pretty common in the wintertime, up to 30 to 40%. And that's all I have. And the main takeaway messages are the near bottom upwelling at the MAB shelf break might be a 3D process, three-dimensional process that dominated by the canyon impact. And then downwelling, if a downwelling event occurs right after an upwelling event, and that usually can cause very strong bottom intensified currents inside the canyon. And in the broader perspective, submarine canyons are an integral part of our regional oceanography, and the processes of canyon upwelling and downwelling can enhance shelf slope exchanges. And thank you. That's all I have today. I'll be ready for some questions.
Kathy,
Yeah,
I think you're muted.
Yeah, thanks, Danielle. I think what we're gonna do is, Kat, were you trying to talk? Sorry.
Thank you so much, Daniel. If anyone has any questions or discussions, go ahead.
We'll just make it sort of a free-for-all. So just jump in and discuss, and yeah.
Hey, Daniel, nice talk. The contour plots that you were showing here.
Which? Sorry.
Maybe go back a few slides. Keep going.
Okay. I'm not sure which screen I'm sharing with you now.
So I see,
This
Yeah,
Looks like your desktop, yeah.
yeah, like slide 32.
32. Okay.
So what depth level is that figure at?
Oh, I'm sorry. So this the bottom layer
Of the
from
model.
Yeah, of the model.
Okay.
So it's about like 10 meter above bottom. Well, so it changes from location to location, but usually the bottom is somewhere between 1 meter to 5 meters. But I think the way I did it was I make sure that it's about the bottom 10 meter or so.
Okay. And so then is the model here, is it able to then get to the very bottom of the canyon?
Yes.
Okay.
So so that's kind of ties to the vertical layer setup. So here, if we look at the vertical layers,
Yeah.
we kind of scrubbed those intensified layers near. It's hard to see here, but if we zoom in, you can see more layers near the bottom.
Okay.
So we made it such a way that because we want to resolve the bottom processes.
But I guess, yeah, so like this is showing the layers through just the canyon, but then you have the model is over the whole shelf.
Yes.
But the model's still able to get good resolution within the canyon.
Yes. So this is the resolution distribution.
Okay.
So the blue ones are meaning high resolution, right? It's like smaller than 500, above 500 meters in this whole region.
Okay.
And then the lighter blue maybe a kilometer or so. So it's
Okay.
yeah.
I have some follow-up questions. Can I just keep asking?
Wait, what was the vertical resolution there?
So near the bottom is about 1 meter. Near the surface is very high as well. So what I'm talking about is right around the sharp break. So if we look at the sharp break depth, so the vertical resolution is about 1 meter near the bottom there.
So
but in the middle of the water column it'd be bigger than that.
okay. So some of the models that I'm familiar with within the Mid-Atlantic are Doppio or Espresso or what's the Stevens model, NY Hops. Are you familiar with those models?
I've checked some of those results.
How could you comment on those those models and their resolution with respect to the canyons?
Off the top of my head, I think as I remember, Espresso had about 6 kilometer resolution near the sharp break. So, and if we think about the size of the canyon, it's about on the order of 10 kilometers. So that's not sufficient to resolve.
Okay.
And that's why we put like 500 meter resolution also near the canyon.
Right. Okay. Good. All right, and then last question. On one of your final figures, number 42.
Okay.
So can you maybe just blow that up a little bit?
Yes. I'll put it on slideshow again.
Sure.
Yeah.
Okay, so do red and aqua, if you add them up, do they always add up to 100?
Yes. So I just did it very simply.
Okay, so either you're upwelling or you're downwelling. Those are your only two flow regimes.
Yes, but I think they might be we need like a middle range, like a arrow range or something.
Okay.
But in this figure, I did not do that.
Okay.
Just use positive and negative at the cutoff.
You mentioned here that there was, clearly significant timeframes in the winter where there was upwelling.
Yeah.
The upwelling winds aren't really there as much as they are in the summer, but the density or the stratification also isn't there either. So I guess that reasoning why it would make it a little bit easier in the winter to get upwelling?
So here we just use that basically the sign of the cross shaft as its gradient. So usually in the winter, when we have very strong westerly winds, we just have sea surface killed seaward. I think that's why we have more upwelling there. And then in the summer, we have southwesterly wind. And
Yeah.
so in July, we have more of that too. So this is not from my model run. It's from just based on the long-term data from HiCom.
Gotcha.
Because 20-something years, we just cannot afford to run model that long.
If you take a detailed look at the time series, the strongest events are in the winter time.
Oh yeah, it's always near January, December.
Yeah, because you probably get the greatest storm activity in the flows. Yeah.
Nor'easters.
Daniel, can you go to your conclusion slide again? So I guess are the measurements that we're making within Marcus now, are they capturing the dynamics of the canyons or to integrate into the models, or do we need more measurements? Like it seems like the canyon it seems like it's such a difficult place to measure things, and so it'd be very expensive. So yeah, like are we currently capturing what's happening there on a regular basis?
Thank you so much for the question, Hugh. That's something that bothered me a lot in my PhD study. So that's something we found. It's very challenging to measure the canyons because the flow is complex and it's fast, and the law processes. It's very hard to capture with just one glider. And also, as we just saw, a lot of, like for example, the canyon upwelling plume that occurred on the shelf. So you need a larger spatial coverage in order to capture that feature as well. So with the work we have done so far, most of the time we put one, and this one time we put two gliders inside the canyon. So we did not really capture the evolution of the upwelling plume itself. But within the canyon, we can confidently say that we got evidence of upwelling event and downwelling event, and that's the most we can say. But we don't have like the flow measurements or the near bottom measurements, because the glider would avoid the bottom. It would come back before it hit the bottom layer. And a lot of interesting process we see that occurs near the bottom.
Okay.
So it's just in the future, I love it if we can have a well-designed, a larger observation campaign just to study the canyon processes.
Okay. So then building upon that, so Dunlai, I think you were involved heavily with the, I guess, lobbying to bring the Pioneer Array to the southern end of the MAB. Can some of the Pioneer Array assets be utilized to study these canyons?
It certainly is one of the science motivations for bringing the Pioneer Array to this region. So we're working on the detailed design of how it's going to be implemented in the coming months, and I think placing some assets in the canyons will be and obtaining that longer term observation will be very helpful for both understanding as well as producing the data that's needed by these data similar models to capture what's happening at the shelf break there.
All right. And so I guess what if I were to talk to a fisherman who's goes out to the canyons to fish, what's a nugget we could offer to that person from your findings?
I would say go there when there's some sort of upwelling favorable winds, which means southwesterly wind or
Okay.
northwesterly winds, and go to the north side of the canyon.
Okay.
So
All
because
right.
that's where the upwell water is, that's where the nutrients are.
Where the nutrients are. Okay.
Yeah. So hopefully they can attract the fish.
Yeah. Okay.
And on the
good.
flip side is that the fishermen has been fishing these canyon regions for a long time, so they have an idea of where the fish are,
They love the height of the canyons.
and I think we can now piece together some of the understanding we have in the physics side with how the fishing has been done traditionally around these canyons to see if we can make sense of what's going on with the relationship between the physics and the ecosystem.
Yeah. So AIS is used to track vessels, but I think fishing vessels require they carry different transponders.
That's such a good idea. We can with fishermen, if they're out there, we can make some measurements.
Well, right, or can you look at the pattern of where their vessels are, to see kind of the idea like where the fish are.
Oh, that's a
correlate
good idea.
The physics that we're seeing.
Yeah, that's a really good idea. I love to. I'm very interested in seeing that actually.
I think it has to be a collaborative effort with the fishing industry to do some type of analysis like that.
Just based on my brief conversation with a buddy of mine who is a big fisherman, and they love the canyons and they always go near the head of the canyons. And I think oftentimes they actually go to, a little bit north of the canyon to get fish. But I need to make sure that'd be interesting to see if there's any statistical patterns there. Like during certain conditions, they catch more fish at certain locations.
And also depends on the specific fish.
Right. Yeah.
What temperature they like, that sort of thing. Another thing I thought is so if the two canyons were close to each other, there might be some exchange of larvae or organisms between those two canyons. Because when you got upwelling from one canyon, for example, Baltimore Canyon and Wimbledon Canyon, which are close to each other, that dense water, when you got close to Wimbledon Canyon, that will go offshore, go downslope into the canyon, the next canyon. That potentially that could mean that, I'm just speculating right now, that the ecosystem might be similar, the species might be similar within those canyons that are close to each other because of that reason.
Yeah, because you were only able to study the one canyon at the time, right? So I guess are there interactions between the canyons?
Yeah. And there's definitely interaction between the canyons, as we can see here, for example, right? The upwell water from this canyon just got to that canyon.
It might be relevant in thinking about how do bottom southern species propagate northward. Because in the normal sense, it's a from north to south flow, and you can accomplish that for northern species going southward. But this could be a mechanism to propagate from south to north. Great, that was fun.
Yeah, any other questions, guys, before we sort of wrap it up?
Just a comment, I like the whiteboard slide. Reminds me of years ago working with Scott, not on whiteboards, but on bar napkins, on thesis and the early stages, no joke about what was going on in the 90s, what was going on with the upwelling centers along New Jersey, and trying to figure out why they were there when we didn't have a good bathymetry data set.
Yeah,
we got that good bathymetry data set, things got a lot clearer. So as to why we were seeing what we were seeing.
Yeah, thank you, Mike. Yeah, I had that experience too. I worked with Scott once at my library. We would make drawings on the whiteboard.
There you go.
and for this one, I was living in a rush near the end of my dissertation. I'm gonna make a computer version of this.
I kept those napkins for years because they were, that was just, that's what a lot of good physics was discussed in those days about those upwelling centers. And it was pretty cool.
Thank you so much again, Daniel. We have a few other speakers lined up for the summer, and we will send out that login information next week. If you or someone you know is interested in doing a science talk, please contact Mary. Mary, and her email address is mary@maricus.org, and we'll get you on the schedule. So thank you so much for attending, and thank you, Daniel, for presenting.
Thank you. Thank you, everyone.
Take care.
Yeah.
Thank you.
Yeah, that was
Thank
super fun,
you
guys. Thank you.
Thank you.